All right, did everyone get the homework? And we have some more to say about the fundamental theorem of calculus today, but today instead of taking a graphical approach, which is almost entirely the approach we've taken so far, we're going to take a slightly more algebraic approach. So that's the deal. Let's just recall what the fundamental theorem of calculus says. Is my thing working here? I don't know why this is dead or something. There we go. Here's a nice quote as well from the authors of our book. We are not learning F now, but we are still calling this part one because there's more. There is a part two that we'll tell you more about later. Isn't that a nice quote? Yes. Yeah, what would you like to be, though? Would you like to be equipped with, like, objects or knowledge if you were stranded on an island? You can, right? Would you like fish or like the ability to fish? Would you like things you can lose or things you can't lose? I don't know. Actually, I think I probably want some food or something. Yeah, this is a review, right? Do you agree that that's the fundamental theorem of calculus?
Yeah.
We've done it. Oh, you wanted to write down the quote? Yeah. Okay. All right. I think we have kind of skated over some of the details of it. Just the question is, when you're dealing with this situation, like we've had the t's, we got an a, we got x's, we got an f, right? So there's a lot going on there. And as we look at some of these, we're actually going to like plug in some functions here. We're actually going to mess with this letter. We're going to put some different things besides x up here today. And I want to make sure that as things get crazier, you have like a firm foundation, okay? The question is, do we have the derivative of an integral? That's a good question to ask. Ask if the fundamental theorem of calculus applies in a certain situation. We better be having the derivative of an integral, just kind of like on the face. That's a high-level observation. We need to make sure that the variable of the differentiation matches this upper limit. Is the lower limit a constant? Then, if so, then we can say that the answer is just this integrand with replace this x. Okay, so I want to make sure if you have any questions about why certain letters appear in certain places in that formula, that we like clear them up right now, because things are going to get crazy. Okay, so again, theoretically that's just a review. I have a couple points of emphasis because we're going to be pushing symbols a lot today. Yeah.
So wait, why is it f of t instead of f of x?
Yeah, can someone refresh our memory about why f of t there? Yeah, do that.
We're not actually looking at what x is. We're looking at what t would be in your theoretical little rectangle. Like, this t.
So
the t isn't what x is in the function. It's another function. Like,
yeah.
it's not the same thing as the x. It's something else that you plug into the f of x.
Yeah, just let's give some names to these things. I don't know if you remember this, but we called this thing right here. We call it like big F of x. Does that ring a bell?
Yeah.
And why is that a function of x? Well, it's a function of x because if you give me a number, what do I do? If you give me like a number like 5, if you say I want x to be 5, well then I think what you just told me is you want me to go from whatever a is to 5, integrating under the function f of t. Now, it'd be weird to say f of x dx because the x you gave me is x equals 5, but it's not necessarily true that x is always 5 here. As we go through that integration, x is all values between a and 5, right? So this is kind of like very analogous to like when we had a sum, we use that local, I like to use the word like local variable. Here we're using the word dummy variable. Inside the sum, like k makes sense. That the variable, what do you call it, the iteration variable or something like that. The k makes sense. We're stepping through. But if you're sitting outside the sum, if you have a summation, and someone asks you what k is, you don't have anything to say about that, right? Because it's like local to the sum, right? It's like saying, like someone came along and was like, sum equal from k to equals 1 to 5 of, k squared or something like that. And someone was like, what's k? Like, what? What are you even saying? K is all numbers between 1 and 5, right? Like, does that make sense? Is this a function? No, it's not. This is a number. It comes out to a single number and we could evaluate it. You know what a function is, though? This. Right? And if you ask me what kind of function is it, I would say it's a function of n, right? The only variable here really that's up for grabs is n, right? Does that make sense? So the same thing here. T is just like a little iteration variable that runs through the integral up to your choice of k, of x, right? So this is really truly a function of x, this accumulation function, right there. But this just kind of keeps the time for us inside there. All right. So we'll play around with that some more, but those are the right letters in the right spots. So we'll start with, of course we'll increase our level of complexity on these, but let's start with this one here. This is not a trick question. You are simply to write down the following. Yes, Amy. Oh. It's okay. You're forgiven. We'll be right back, everybody. Yeah.
Is the f of t in the integral the same function as f of x?
Yeah, little f here is little f here. Exactly. Yeah. And we'll actually demonstrate that here in a second. So, evaluate it at different places along the way, right? But, so what is, like I said, this might seem deceptively simple, but all we're saying, let's go through that checklist here. Do I have it here? No, I don't have it. Is this the derivative of an integral? Yes. Is this, what was my checklist? Is this top limit of integration? Does that match this variable here? Is the variable with which we're taking the derivative with respect to the same as the top limit of integration? The answer is yes. So we're good. And then, last but not least, is this a constant? And the answer is yes. So if so, then what can we write down? Does the fundamental theorem of calculus apply? Yes, immediately, directly. Let's just write it down. What is it going to be? 1 over 1 plus t squared. All right, that's all. And you might be thinking, well, there must not be very much more to say. That seems like there's not even, like, why was this worth even talking about? But we can like throw some snags in too. Keep in mind that would be the same answer, whether that was 0 or whether that was like 100 down there, right? I just want to remind you of the chain rule. And let me just emphasize again that this is it looks a little weird here, but the chain rule might apply because we are taking a derivative. So if this happens to be something that's more complicated than x here, like say the upper limit of integration is like 2x. Well then, how do we handle that situation? Because obviously it's not it's derivative with respect to x, not like 2x. So if this is some other expression instead of just x, well, we can handle that. It's just f of whatever that is times the derivative of that thing. It's just the chain rule, isn't it? Because again, let me emphasize, this is a function. Normally, it's a function of x, right? It's an accumulation function, and the top limit of integration is normally x. We would write, this is an accumulation function, its argument is x. Well, now its argument is u, right? So how do you take the derivative of a function with respect to u? When, or with respect to x, when the actual argument of the function is u? Well, the chain rule applies, right? So the example to show, a simple example to show would be this one here. Right? And we handle this situation. Again, we're just mainly, doing this in the name of like getting comfortable with like the pieces of algebra here, the letters, the objects. So I mean, we can really do the same thing we did before. We have a derivative of an integral. We have a constant at the lower limit of integration. We have these not quite matching, right? But our first guess might be to say, well, it's maybe just cosine of x squared. And that's not bad, except, of course, the extra piece that we just are emphasizing here now is that you also need to apply the chain rule and multiply by 2x, right? The derivative of the u, which in this case, again, I know I've said it a couple times, but I think that we can't emphasize it too strongly, that this thing inside here is a function of this upper limit, right? That's the thing this is a function of. So what is this a function of right here, minus the dx here? That's a function of x squared, isn't it? When you look at that, I want you to see that that's a function of x squared. Now I'm going to leave the answer that way. There's one little snag we can add in. How do we handle that situation? Can we deal with that? I mean, we have, with our checklist, we've got the derivative of an integral. We've got the variable of integration does match the variable of differentiation. So that's cool. The upper limit of integration, or the lower limit in this case. But the lower limit is not the constant. So I think we're clear on how we could deal with this, maybe. How can we make what we want happen? Yeah, yeah.
Can you just like let f, well no, 5 and x, then make them minus 1?
Yeah, I think. And then the rest is kind of history, right? What's that? 3x sine x? Negative, with a negative out front. Not too bad. So we dealt with the chain rule. We dealt with what happens if the limits of integration are switched on us. What other snags can we throw at you? How about that guy? Oh, that looks like fun. Maybe we can kind of do all of that at once here. Yeah, no, we need a constant in one of those things, it seems like. No. But I like, again, I like the idea, like we just used a second ago, of using properties of integration to get where we need to go here. How about we, I don't know if I can lead you to the first step on this or not, but if we want a constant as the limit of integration, I think we can maybe split this up into two integrals, right? So I'm going to split this into two integrals. 2x to give me your favorite integer, or any number. 4, 5, okay, 4. Of 1 over 2 plus e to the t dt. This result is the same as this result, right? By the way, the fact that we can do this is because these have the linear property. You can just say d dx of the whole thing if you like to, but they're the same. From 4 to x squared. This guy I think we know how to deal with because we've already thought about it today. You know, the chain rule will apply. And this guy we've already thought about today. So see if you can finish this off now. I mean, I feel like that was the big move.
Is there any like limit to which, not limit like math limit, but like can you choose any integer?
Yeah. So I mean, Josh chose 4, but. But I mean, I would probably just use 0, but I just want to make sure, I do want to have you realize that that is actually an arbitrary choice. When we go to apply the fundamental theorem of calculus in a minute, when we actually do the application of the fundamental theorem of calculus, as you know, the value of that a doesn't matter. As long as it's any constant, will be good. You know? So make it 0, make it 4, whatever. Doesn't matter. So this guy over here is what? The opposite of 0 to 2x. There we go. So this guy is what? Negative 1 over 2 plus e to the 2x. Yeah, throw a 2 up there just for fun. Because of the chain rule, right? And that guy over there is 1 over 2 plus e to the x squared times 2x, yeah. And I don't actually see a real great way of doing anything more than that in the way of simplifying, right? I mean, these aren't like denominators or anything, so yes, Peter.
Factor, like would you want us to factor out the 1 over 2 plus c? Oh wait, 2, sorry.
Yeah, I mean, the fact that these are different functions here makes everything kind of, I mean, I don't think we can really write any better. So. All right, so, and that is in fact like really maybe the trickiest situation we can give you. We've got the chain rule going on in both places. We've got to split it up. We've got to flip this, right? And really we're doing all this in the name of you just getting like comfortable with the algebra and the symbols and the objects we're working with here, right? Can you understand not just the moves, but like why they make sense in terms of the fundamental theorem of calculus and in terms of our properties of integration that we've learned prior to this? Hope so. All right, give these a try. They're not, some of them are, most of them are easy. Give them a try. Yes, sir.
This right here is like big F. Oh. Yeah, you love that. Yeah, you like the function of u. So what is the derivative of a function with respect to x? Well, the derivative of a function of u with respect to x is just the derivative of the function with respect to u times the u, right?
Let me say that again, right? The derivative of a function right?
Yeah.
Isn't that what we're dealing with? Isn't that f prime of u of x times u prime of x? That's just the chain rule, isn't it?
Oh, yeah.
So all I'm saying is that is in fact the situation we're in. Right, where this is what we mean by big F of u of x. So it really is just the chain rule that we know and love. I wrote the result on the slide 2 slides ago up here in a slightly different notation. Maybe you're more comfortable with why the chain rule works here when we talk about it this way. I mean, that integral in there is just this big F of u of x. I don't know if that helps other people see that better too. I mean, certainly, you don't even care what big F is, right? If we have this situation, you know that that's just the chain rule. Now, but if I told you big F of u of x is just this guy, then I think that's the result we were looking for. Yes, cube. We have like full permission to make these as messy as we like, right? Because you say you're skipping school, really? All right, helping out with these here. Ian just named the first result listed off. Go ahead.
Thanks, Ian. 2 2x cosine x squared.
Cosine x squared? X squared, yes. There we go. All right, good. Babesh. For B, are you ready to take it or no? He's got it. Cosine of 2x plus 1 times 2. I think I agree with that. Are you okay with, by the way, this new instruction? It's the same as the old instruction. I just want to make sure you're clear with the notation. Yes? These are kind of all accumulation functions we're kind of looking at, right? And we're taking the derivative of those things with respect to x. That's what we mean by big F prime of x. Okay. Copy Y. You want to take C if you're ready? What do you say there? You can just give me the final answer. Sorry, negative cube root of tangent, sorry, of x squared, okay. And times 2x somewhere in there. Yeah, exactly. And then, Steven, how'd you do on D?
4 times root 3 plus cosine squared parentheses 16x squared.
I think I like that. Is that? Good. All right. Now I don't think I don't have these on the PowerPoint, but I want to talk about some interesting problems that are on the worksheet that we just passed out. I think some of these are. I guess not. All right. So, and there are some. I feel like there's one or two like this on the homework on some of these. Let me give you at least a hint on some of these. I'd like to get you in the right direction. So even though you don't know on number 1A, for example, you don't know what function has a derivative of e to the x tan x. You don't know what function has that as its derivative. Except, maybe you do. Like, how about these functions? Like, if I asked you, what function has as its derivative 2 cosine of 2x plus 1, you could write this. Right? Right? I mean, yeah, I'm kind of going backwards on you. So if that's the derivative, what would be a good way of writing the function? Y? Wouldn't it be like the integral of... Okay.
I'm trying to like move this, right? Would you
Now, this one doesn't have the chain rule involved, but yeah, you're right.
I wouldn't be able to know like besides A, right?
No. Well, yeah. Let's say that right now. We don't know what A. You're right. Okay. So good. Let's say that. But we're gonna put what are we gonna put as the integrand? E to the. Maybe e to the t, or whatever dummy variable you like. Tan t dt. This ensures that when we do take the derivative of y with respect to, what do you want to put up here? If we take the derivative of that function, so here's a function, it's a function of x, right? If you take the derivative of that, do we get e to the x tan x? I think so. Now the other thing that needs to be true is that when y is 0, when x is 8, y is 0. How can we make sure that happens? Go ahead, Kate. Sorry, Josh. Tell me why that makes sense.
Because when you plug in 8 for x, when you integral, you use the version 8 to 8.
You have the arbitrary choice of a to be any constant you like. You'd like it to happen that when you plug in 8 for x, that you get 0. I think Katie just did it for us. Yeah? That was more than a hint. That was a more than a hint on A. That is the answer to A. All right. So think about how you might do B as well in similar fashion. Except notice that it's like with the initial conditions there, y equals 4 when x equals -3. That's a little different. But also keep in mind that we like have the ability to do other things to this function. Yes. There's a okay. Number 2, I'd like to just try and think. Number 3 is an interesting one. Might have to talk about that one in a minute. Here, I'll let you guys work on 1, B, and number 2 though for a minute. Well, there's no plus C. That's the function. We're done. C is 0. Yeah.
To evaluate this, I mean, just look at non-calculated value.
Guys, I think you're overthinking this a little bit. Let's just think, for some of you on B, let's just follow the model from A just a little bit here. If you wanted it to be y equals 0, wouldn't you say this is the answer? Right? That would be the answer if you wanted it to be true that certainly the derivative of that will be the function right in front of us. And if we plug in -3 for x, we'll get 0 for y. Oh yeah. So how about just that? Doesn't that meet all the characteristics that are mentioned? We've come up with a function y that has the correct derivative, and when you plug in -3, you get 4. Done. Yeah. Let me say a word about number 3 just to get you started on this, and I think there's one on the homework too like this as well. It says find f of 2 if the integral of from 0 to x of f of t dt is equal to this. All right, so now it would be nice, guys, if we're trying to find f of 2 to have access to the function f of x, right? Do we have access to the function f of x? We don't, right yet, at least. By the way, what is this? This is not f of x. This is like, I don't know, like big F, right? This is the accumulation function, which, by the way, in its own right is like an interesting idea. It's claiming that for some little function f, little f, that this gives the area under the curve for that function. This is an interesting assertion. Good, but how do we get little f of x? Is there a way we can recover it? What would you like to do, John?
Little f is the derivative of big F, so I take the derivative of this integral, which is this.
Yeah, let's like d dx this thing, right? If we d dx this whole equation, then on the left we just get f of x by the fundamental theorem of calculus. And on the right we get something, which is f of x, little f, right? So that means you'll have to take the derivative of this, but once you have it, I think we'll be able to figure out what f of 2 is. Yeah? So taking the derivative of both sides of the thing given is, I think, the route to getting that one. That's my hint on number 3. And I have no hint for you on number 2. I think we can do it. I'm not getting lost in all the algebra.
Oh, that's a plus. Yeah, that's x.
Yeah, it's good to take a derivative once in a while. You don't want that.
Okay, so should we reserve 9, 7,
Alright. Homework tonight is from the book, remember. Homework 2 from the book. What's the answer for 3? Yeah. One half times x squared plus 5 to the negative 1 half times 2x squared x. So whatever that is. That'll be 9.
I think I might actually do this
I'll be at school. Usually it happens. I like it.
Bye, guys.
Yeah. Is he getting like a ton of stuff on that one Yeah, I need to be Laura. Will you come to Walker?
No, I need
See
to
you guys tomorrow.
I'm better down later. Yeah, I know. I saw the picture.
There might be,
I forgot about that.
I didn't actually ask this sketch, and there's currently nothing on the so I didn't ask the sketch whether it's meaning that there's no real plan for tomorrow or whether I mean, because we're going to do, I don't know if we're going to plow forward and do the next lesson or not, so. It's kind of an activity thing. I don't want to do it. So, yeah. Have a good break. Don't worry about it. Oh, you're doing test questions. And you're giving me things. Thank you. That's very kind of you, Zachary. Very, very good with psychology. Okay, let me get you set up here a second. So, were you here? You were just not here at all on the day we did corrections?
I had to go for a doctor's appointment.
Yeah, so you weren't here. So the way we set it up is I'll give you a fresh copy of the test in a second, and you'll redo all the ones you got wrong on the test, and you can use your notes, you can use your calculator. So.
I just have a quick question. Do you know if Mr. Davis is going to be in school tomorrow?
Oh, I don't know. No, I don't know.
So would you be willing to take MHS shirt order form instead of him, or
Oh, what form?
MHS shirt order form about like money and stuff?
For you or something?
Well, for like Simon gave you the